Hello, I'm René Grothman, the author of Euler's Toolbox. In this video, I want to show you how to do linear problems in Euler's Toolbox. Here is a problem, and we will solve it using the simplex function and using a step-by-step calculation. First of all, we have to enter the problem into Euler's Toolbox. We have to define the matrix A, the right side B, and the target function, which is a row vector C. So A in this example is 1, 1 for the first line, 3, 4 for the second line, 400, 200 for the third line, and 1, 0 for the fourth line. We don't have to enter x, y greater equals 0 because this is implicitly given in the simplex algorithm. The right side is 90, 360, 24,000, 24,000, and 40. The target function is 450, 150. It must be a row vector. Now we can start the simplex algorithm like this. And we have to tell it that it should maximize the target function. If it is to minimize the target function, the result will of course be 0. Let me show you the help for the simplex function. Just double click on simplex and the help window will open. You have here the simplex function, some examples at the end, and an explanation. As you see, we minimize under the condition A times the vector less equal B, or greater equal, or equal, and the condition x greater equals 0. Later I will show you how to enter A, B, C from a file. Now we want to solve the linear problem step by step using the simplex algorithm. We need to set up the simplex tableau. Let us start with M, A aside of B. Now we have the matrix A, and aside of that we have the matrix B. We need also slack variables. And now we see that the matrix gets too wide. So we select another format. We take a fractional format with about 10 places for each number. That should do it. We need below this matrix the target function C. And now we can start the simplex algorithm. Our first pivoting element will be in the fourth line, the first element, this one. There's a function pivotize M, which needs the matrix, the line, and the column. As you see, we have still a valid basis, and we have now the unit vector in the first column. Next, we need to handle the 150 at that place, and we need to select the pivot between these elements. The correct pivot will be that one, so we pivotize the third row and the second column. We have now found our optimal value. All remaining target values are negative, and we can now read x is 40 and y is also 40. Let me show you a few tricks to make life easier. First of all, let's start a new command block with an empty line in front of the definition of m. Now, if I press Shift Return, the block of commands starting from the command after the empty line will be re-executed. Shift Return like this. Assume we make a mistake in the second command. We take the third row instead of the fourth, and we immediately see that we have non-feasible points. The right side must always be non-negative. We fix that by entering 4 here and pressing Shift Return. Now, likewise, if we do an error here, just like that, we get non-feasible points. We fix it and press Shift Return, and doing all the Gauss algorithm all over again. There is another way to start the new command block, which is more beautiful. Press F5 to open the command window and enter 3 minus signs, and you get a horizontal line which starts a new command block too. You can't get rid of that empty line then. Next, let me show you how to enter the matrices from the file. We start a new command block again, and then I show you the file. Here it is. We have the matrix A, the right side, and the target value. You can use any number format with decimal dots here, and you can have comma-separated values. The condition is that before the next matrix, before the right side, we need to have an empty line. If you have it like this, you can read the 3 matrices in the following way. You open the file example data. You read A, you read B, and you read C. That's all. You should close the file after you have read it. For the next example, we have selected equalities and inequalities. Moreover, we have released the condition x greater equal than 0, and otherwise it is an ordinary linear problem. We want to read the problem from a file. Here is the file. We have encoded the problem in the following way. The first line reads x plus 2y plus 3z equals 0 is for equals 3. The next line is the same, and this line reads x plus y is greater equal 1 for greater equal minus 2. And then we have y plus z is less equal minus 1 for less equal 5. The target function is 214 filled with 2 zeros so that we can read the whole file as into one matrix. The restrictions read X is not restricted, Y and Z are restricted, greater or equal than 0. 1 stands for greater or equal 0, minus 1 for less equal 0. So let's read that into a matrix. I forgot to tell you that example2.dat data must be in the same directory as our notebook. Otherwise, we have to add a path to the file. Once we have that matrix, we can try to extract A, B equation and target function from the matrix. For instance, A will be M 1 to 4, row 1 to 4, and column 1, 2, 3. B will be the row 1 to 4 and the column 5 of M. Of course, the target function is M, the 5th row and the first 3 columns. The restriction function is the 6th row of M and the first 3 columns. The equation vector is in the 4th row and the first 4 columns. Once we have that, we can use the simplex algorithm with A, B, and C as before, and the equation vector EQ and the restriction vector R, and we want to maximize. We get this solution. The value of the result is C times X. Now let's try the minimum. Will be that, and the value is 3/2. So much about the simplex algorithm in Euler's toolbox. There's also another toolbox which is called ILP-solve and is very, very good for integer linear programs. Please have a look at the tutorial to learn more about that. Thank you for listening. Yours, René Grothman.